Okay, we're going to jump into section 2.2 now. Specifically, we are going to spend this time together looking at our introduction to functions. Now, one thing I want to point out real quick, this is probably going to be one of the longer videos that you'll run across because there's just so much content when it comes to functions that we really need to go through because a lot of it is just setting the stage for the rest of the semester, for the rest of the coursework that we'll have up to this point. Previously, that a lot of what we've been doing has been looking at graphs or specific applications. It's a lot of arithmetic with certain things. This is really where we start to get into the real math, I guess, if you want to call it that, the real algebra and kind of abstract concepts and how they all apply and work together. And so I just want to let you know that's probably going to be happening a lot more as we go through the rest of this course. So hopefully this will be just a nice way for you to kind of whet your appetite. Although I don't know if any of you actually have an appetite for math, so I don't know. We'll find out. Anyway, here we go. We're going to go into our introduction to functions. I just want to go through some of these notes real quick. You're going to see there's like 3 pages of notes here. So bear that in mind. I'm going to try to go through this quickly and start jumping into examples, but I do want to point out this is one of those longer sections. Okay. So the definition of a function, it's a set of ordered pairs in which no 2 ordered pairs have the same first coordinate and different second coordinate. In other words, if you think of just xy points, we talked last time about the Cartesian coordinate system or 2-dimensional coordinate system. If you think of xy values or xy points, what we're basically saying is you cannot have 2 of the same x value for a function. Okay, so if I were to think about a straight line on a coordinate system, that actually would be a function because you don't see any x values represented multiple times. You can have multiple y values represented multiple times. We're going to see this a lot probably coming up, but a parabola, for example, it looks like a giant U when you draw it. That actually is a function, but it has, if you look and draw a straight horizontal line through the parabola, you'll see that there's 2 y values that show up, or I should say 2 of the same y values that show up. However, there are only 1 x value for each y value. It's kind of weird, but hopefully it'll make sense if you as we get a little further into this. So this you can see it with actual functions when you graph them. You can also see a function as dealing with sets. So in this case, this is the set 2, 3, 5, 1, minus 4, 3, 7, 11. This is a function because if you look at all of the x values right here, there's not a single one that shows up twice. They're all different and distinct x values. If you look at this set, this is a different one. This is not a function, and the reason why is because I have a 5 that shows up as an x value in both places. Okay, so this kind of in a more simple way, I guess this is like the more simple way of thinking about functions. If you can represent any 2 x values that are exactly the same, you just know that what you have is not a function. It might be a graph, but it might not be a function. Circles, yeah, so I mentioned this here. Circles actually are not functions. And again, the reason why is because you actually have multiple x values represented with the same y value. So, for example, if I were to draw a circle, I'm not going to do that for you right now, but if I were to draw a circle and stick it on the coordinate system, say my center is at 0, 0, and I've got a radius of 5, okay? What that means is that at the point, now think about above the origin, okay? Actually, let me just switch to the switch to my board. I'll show you really quick. So here's my coordinate plane. Here's my y-axis. Here's my x-axis. Okay. If I've got a circle, you're going to see my awesome drawing skills here. They're terrible. Okay, imagine that's a perfect circle. It's definitely not. But right here, I have the point. So this is, say, we'll call it x squared plus y squared is equal to 25. So this is a circle centered at the origin with a radius of 5. This is going to be the point 0, 5. I got my coordinates mixed up. 0, 5. This right here is going to be the coordinate 0, minus 5. Okay? But what you notice is that the 0 shows up twice. So because you see there's two x values that are represented at the same time by this graph, this cannot be a function. Okay? So in general, when you see anything that kind of loops over itself like that, you're not going to have a function. It's just going to be what we call a graph. All right, so again, some of these terms we've probably used in the past, but I just want to spend a little bit of time clarifying them or defining, kind of formally, I guess. The domain of a function is a set of all the first coordinates, so x values, generally they're x values, of ordered pairs. We call our x variable the independent variable. And so in statistics, a lot of times if you have to plot or graph anything that represents any kind of statistical relationship, your x-axis will always be your independent variable. You'll probably run across that if anyone takes any statistics course in the future. So the domain of a function, specifically, we're only going to be looking at real numbers. You can ignore anything that has complex or imaginary numbers. The range of a function or a relation is a set of all the second coordinates. So the domain is dealing with all the x values. The range is going to be dealing with just the y values. This is also, if you think in statistical terms, this is called the dependent variable. Function notation, up to this point, everything that we've done, it's been y is equal to something, right? Y is equal to x. Y is equal to 5x minus 3. Y is equal to x squared minus 4. Really all we're doing is we're just changing the way that we say and represent it into something that is a function of something else. Okay, so for example, we would normally say y is equal to, in this case, x minus 1. Here we're actually just going to say f of x. That's the way that you say it. F of x. So in other words, we evaluate the function of x at x squared minus 1. We're going to see some context here in our problems when we go through them, where it's going to say, hey, find f of 2. What this is saying right here is that for every single x value I see in my original equation, I'm going to replace it with a 2. So you're only given x values, and then ultimately you're going to find that this is going to be 2 squared minus 1. 2 squared minus 1 is going to be 3. So f of 2 is equal to 3. So actually, here's really what that's saying, is that I'm finding what the value for y is when I'm given the value for x. So if the value for x is 2, the value for y is going to be 3, the thing that I literally just found. So that's kind of how it works. It's a bit of just a different way of thinking about it, and it's really just in terms of a single variable instead of multiple. Piecewise defined functions, I don't want to take too much time dealing with these, but I will look at them really quick. Here with piecewise defined functions, you are going to have 3 different pieces, or 2 different pieces, or any number of different pieces, I should say. And what you're doing is you're saying that this function will equal one of these. In this case, there's 3. It's going to equal one of these 3 things, but it's only going to equal one of these 3 things within the specific restriction that's given. So in other words, if I have the absolute value of x, I'm only going to use this equation for every x value that's smaller than 1. So if I have x, say, well, let me show you what this would look like if I were to graph it, okay? Let me write this down. Let me just write it while you're here. X less than 1, x squared. I probably should have picked an easier example here to demonstrate what I'm referring to. Minus x minus 2. X greater than or equal to 3. Okay. So let me go to the whiteboard here, and I'm going to show you how to graph one of these. It's not going to be super pretty, but like I said, I'm not any kind of artist here, so I hope you give me a little bit of latitude. All right, so really when you're looking at the values here, so these are kind of our important, I don't want to call them critical values because that's like a different term in math, but I'll just call them like super important values. They're important because those are really the domains for the specific pieces of functions that we're working with. So for absolute value of x, for x less than 1, remember x, the absolute value of x, let me just show you what it looks like, okay? What it's saying is I'm going to have, so imagine, I'm ignoring all this stuff, okay? Imagine that I have a straight line, okay? Ignore the absolute value sign. This is literally equal to y equals x. This is really what it is. So the absolute value, what it means is that if I have anything down below the x-axis, all I'm going to do is just flip it. So it's over the, so it's positive. Okay, so this is negative, which means that it has to be positive here. So that actually is the absolute value of x. Now, what I need to do is I need to look specifically at what they give me in terms of the restriction. So they say x less than 1. So that means that right around, I need to put a scale in here so we can deal with this here. 1, 2, 3, 4, 5. I don't know if you can even see that, but so what that's saying is that cut it off at 1, okay? And what we're going to do is we're going to leave it with an open circle. It's an open circle because it's less than. If it was less than and equal to, in fact, the next equation is going to be that. We would have a closed circle or filled in circle. So x squared. How do I graph x squared? Well, what I need to do is let's just substitute 1 in for x. So 1 squared is just going to be 1. Conveniently, it actually is going to be on this exact same spot. So that's the cool thing about it. If you want to go ahead and graph it, what you're going to see is that when x is equal to 2, it's going to be 4. So here's 1. Oops, sorry. Wow, that was bad. This is not 1. Here's 1. Here's 2. Here's 3. Here's 4. Right there. So it's going to be at 2. It's going to be 4. And the 3 is actually going to be off the scale. So I'm just going to do that. It's actually a little bit of a curvature, and you can tell I totally missed it. Totally missed my point. Drawing, it's really hard. All right, so this is the first part up to here. This is the second part. And then actually, again, I shouldn't have filled that in. This is actually going to be an open circle here. Actually, it's going to be, sorry, it should not be an open circle at all because it's going all the way up to 3. Okay? And you can't see it. It's off the chart. X greater than or equal to 3. So for all of these x values over here, we're going to use minus x minus 2. So let's just throw 3 in for that. We're going to get minus 3, minus 2, which is a minus 5. So imagine minus 5 is down here. What you're going to have is the function right here. It's going to be a filled-in circle. and it's going to be something like this. Okay. So this is our piecewise defined function. If you were to graph it out, it's kind of crazy when you look at it like that. So again, think about what this is saying. X less than 1, for every x value less than 1, it's going to be everything over here. We're using this function. For every x value between 1 and 3, so just within this tiny little range right there, or domain I should say, the graph is going to be a parabola following x squared, and then for everything bigger than 3 or equal to 3, we're going to use this linear equation, which is minus x minus 2, and that is going to be, it's going to have a negative slope, which means it's going to look like this. Again, I kind of did this a little fast, but I think the book has a couple of different examples as well, so you can go ahead and check that out at your discretion if you would like. So that's really the, I said I wasn't going to take too much time on it, but I decided to. Because why not? If this video is going to be long, might as well make it really long. Okay, let's go back to the notes. The zero of a function, we actually may have already looked at this at some point. We're just kind of, again, formalizing the definition. The value a in the domain of a function f for which f of a is equal to 0 is called the zero. In other words, if you're basically looking for where it crosses the x-axis. That's literally what it means. It is literally just where the function crosses the x-axis. So if you have f of a is equal to 0, then a is the x value that sits right on the x-axis wherever it crosses. Okay. Whenever we solved quadratic equations in the last chapter, so if we had, say, for example, I just used this example already, x squared minus 4, right? F of x is equal to x squared minus 4. If I needed to find the zeros, what I would do is set that equal to 0. So I'd have x squared minus 4. Here, let me show you really quick. So if I wanted to find the zeros, I've got f of x is equal to x squared minus 4. I'd set the whole thing equal to 0. And then I would solve. And you can solve using whatever method you want. You can use completing the square, quadratic formula. I'm just going to factor this because I know it's easy. X plus 2, x minus 2 is equal to 0. And when we have something like this, remember, we're going to set each individual piece equal to 0. So x, in this case, is going to be a minus 2. X is going to be a positive 2. Okay? So those are going to be the two zeros of that function. All right, let's go back. We'll go through, again, some of these examples. The real zeros x-intercept theorem, again, I think that's in the textbook. You don't need to really worry about the formal language here, but again, that's just kind of what it's representing. The vertical line test. Okay, what is the vertical line test? Previously, what I said was, hey, if you think of a circle, right, there's multiple, or I should say the same x value represented in multiple y values. Yeah, and you can't have that in order for it to be a function. There's a really easy trick that you can use. And the trick here is that if you take a straight vertical line and draw it through your function, or your graph, I should say, if you draw a straight vertical line through your graph, if the vertical line touches the graph at more than one place, then you do not have a function. So in other words, you can kind of see this graph here. It actually loops back on itself a little bit. And if you were to take a vertical line and connect it through these 3 red dots, you'll see that it actually connects in 3 different places. It's a perfectly straight vertical line that goes through the function. Now, and again, this applies for anywhere on the function. The vertical line test applies for anywhere. It's not in any specific place. So you can think of the vertical line test as saying at any point on the graph, if there's a place that shows a vertical line going through the graph multiple times, then it's not a function. Okay? So you can say, like, just take a look here real quick. If I draw a vertical line over here, it only goes through it once, but that's not what the vertical line test is for. The vertical line test is for testing every possible point. And usually it's just a way to kind of eyeball if you have a function or not a function. So as you see here, if I were to look at this bottom one, this is a linear function. It actually is a function. And the reason why is because at every single point or every single vertical line that I could draw, it doesn't touch, the graph does not touch the vertical line in multiple places. Okay, so that's pretty much what the vertical line test for functions refers to. Increasing and decreasing functions and constant functions, okay? Again, a lot of this is just eyeballing it. Let me show you a quick example on the notes. So, increasing and decreasing function. Okay. Here's my y-axis, here's my x-axis. Let's just label this right there. This is going to be minus 1, 1, okay? So when we look at this function here, which it is a function, you can see that if I drew a vertical line at every single point, that it's only going to touch the function at one place. What we're doing when we're looking at increasing, decreasing, and constant functions is we're thinking about pretty much like the slope. If you want to think about it like a linear function, right? If you know a line, say this is a line right here that we're dealing with. This right here has a positive slope. Okay? If I did something that was like this would have a negative slope, right? Negative slope. Now the same actually applies in just functions and when we're talking about increasing and decreasing. It's kind of the same idea. You're looking at the behavior of what happens when you're looking from left to right. Okay, we read from left to right. That's just the way that, culturally that's what we do. There's some other cultures that read from right to left. In math specifically, again, there's certain instances where you read from right to left in math, but in this instance, what happens is we're going to look from the left to the right. We're going to follow the trajectory of the graph and to see whether it's increasing or decreasing. So as I move to the right, what's happening in the up and down scale? Here I'm going down, so that means I'm decreasing. Okay? You can think of it as having a negative slope. And it decreases down to this minimum point here. Okay? So here's the minimum. It's decreasing to the minimum point. At that minimum point, it's going to be constant. There is no slope. It's a straight horizontal. I guess calculus is better at defining a lot of these terms. If anyone goes and takes calculus, a lot of this stuff is going to show up again. So you can think of this as almost like a pre-calculus kind of class or discussion or topic. If you were to draw a line that was only touching at that point, it would have it would be a straight horizontal line which has zero slope. And what that means is it's a constant slope. So it's going to be decreasing up to this point, then it's going to be constant here, and then it's going to be increasing. This function is going to be increasing everywhere else. Okay? So that's kind of the idea with increasing and decreasing. And again, maybe we'll go through an example here as I jump into some of the problems. All right, one-to-one functions. We're almost done with the notes, I promise. I told you it was a lot. A one-to-one function, this specifically is dealing with x values and y values in a very specific way. So previously, again, this is the easiest way that I've figured out to remember this. If you look back at the definition of a function, we said there can only be one x value for every y value, but you can have multiple y values. So for example, if you, again, look at a parabola, this is exactly what this is. It's got two values for x, or sorry, I should rephrase this. This is actually, it should say two values for y that give me an answer of 4. That give me a y value of 4, okay? The x value is going to be the same, so, or different. It's terrible phrasing. Anyway, you're going to have multiple y values showing up. At f of minus 2 and f of 2, I'm going to have a y value of 4. Okay, so these are different x values for the same y value. So when I substitute those in, I get the result of 4. When you do a negative 2 into the function, you get 4, and a positive 2, you get 4. This basically isn't a one-to-one function. In other words, a function is defined as having only one x value for every y value. A one-to-one function means that for every x value, there is exactly one y value. Okay? So a parabola does not satisfy a one-to-one function. If I were to draw a straight line, that specifically would be. Oh my gosh, I've been on my whiteboard the entire time, so you probably have no idea what I'm saying. Okay, well, here are the notes. You can pause it and listen to what I just said for the last like 3 minutes. Okay. So one way to test for this, previously we were testing functions using the vertical line test. A horizontal line test is a way that we can determine whether or not a function is one-to-one. So if I go back to my whiteboard, which I literally was just on for a while, sorry about that, we have, again, this is just a quick example here. Here's my x, here's my y. If I have something, for example, let's just do a parabola. We'll do x squared. There it is, like the sound effects when I draw. So here's x squared. Y is equal to x squared. You can write f of x is equal to x squared. I don't really care. It's the same thing. So when you look at this, if I draw a horizontal line through this, you're going to see that it actually touches at 2 points. So this fails the horizontal line test. Okay? It passes the vertical line test, which means it's a function. This horizontal line test is more specific. It's just saying that it's not one-to-one, not a one-to-one function. It's a function, it's just not one-to-one. All right, I am not going to go into the greatest integer function or floor function. Why not? We're here. Let's just do it. I'm debating as I'm going through this. Do I want to talk about it or not? The floor function is, well, it's really what it is. There's actually something called a ceiling function as well, ceiling and floor function. So normally when you round, say if I had the number 4.5, right? Normally when we round 0.5 and up to the next highest integer, okay? The floor function basically means that unless you're sitting specifically on an integer value, so 1, 2, 3, 4, 5, if you've got any decimal point, you're always going to round down, no matter what. You could have 4.9999999, but the floor function of that number means you round it down. That's literally all the greatest integer function or floor function is. That's it. Take whatever decimal you get, floor function it, you round it down. Okay? Ceiling function is the complete opposite. It just means round it up. So that really is just what those two things are. Again, these are just very distinct functions. I don't even think that there's probably going to be a question on an exam or homework assignment, maybe on a final exam, but I really don't even think that that's even a possibility. All right, let's go to back to our whiteboard and let's go through some examples, a bunch of examples, in fact. All right, so Question, well, let me go to my textbook here. In the textbook, it's just such a long section. We'll look at question 6. This is asking us specifically whether the given value of x is in the domain. Okay? So 6, we've got g of x is equal to 1 minus x squared. X is equal to minus 1. I will give you a hint on this part, this specific question. The thing that you need to keep in mind that have really strange domain restrictions, they're going to be piecewise defined functions, piecewise defined. They'll be rational. Rational expressions. So previously, if you've had, remember last chapter we talked about if you have a fraction, so 1, say like x minus 2 over x plus 3, at x equals minus 3, the function would fail because we cannot have a 0 denominator. That's what this is referring to, okay? Or a radical expression as well, okay? Remember, the domain is only dealing with real numbers. You can't have imaginary numbers. So if you have a negative value under a square root, you will have a failed domain. So in this case, when you look at this particular problem, it's none of these three, which means this is in the domain no matter what. So x equals minus 1 is definitely in the domain. And one way you can prove it, you can actually go ahead and just substitute the value in. G of minus 1 is equal to 1 minus minus 1 squared. This is equal to 1 plus 1, which is equal to 2. Oh, sorry, actually I just totally screwed that up. This is a minus. 2 of those and 1 of those is 3 of those, which is a minus, so this is going to be 0. Regardless, it makes no difference. I just did my arithmetic terribly. So we've got minus 1, 0 is going to be the point, right? So in this case, x equals minus 1 is in the domain, okay? In other words, x equals minus 1 doesn't cause our function to fail. Again, that's kind of the way I like thinking about this. Will it cause my function to fail? Will it give me something that is completely ridiculous? Let's do number 10. Here's an example where it will happen. Yeah, let's do, so capital F of t. Again, this is just kind of a different way of writing a function, but it's the same thing. T3 plus 8. And we're looking for t is equal to minus 2. All right, so let's substitute the value in and see what we get. F of minus 2 is equal to 1 over minus 2 cubed plus 8, which is equal to minus 2 to the third power is minus 2 times minus 2 times minus 2. I've got 3 negative signs, so it's going to be negative. And that value, when I multiply it, is going to be 8. So this will be negative 8 plus 8, which is equal to 1 over 0. Yikes. We do not want that. Okay? That is a big no-no. We've got a 0 in our denominator, so what this means is that t is equal to minus 2 is not in the domain. Okay? T equals minus 2 is not in the domain. All right, let's keep moving. Let's do number 20 is asking us to find a 0 of the function. Okay? Now I'm going to show you a trick as well to solve these a little bit more easily. You can graph it if you've got a graphing calculator, and there's actually, this is squared. There's actually a function that'll show you the roots. Roots or zeros or whatever you want to call them. They mean the same thing. And so question 20, it's saying to evaluate. Evaluate it here and determine whether or not it's a zero of a function, so x equals 0. So what we're going to do is literally just substitute this in. X equals 0 means that we're looking for f of 0, okay? So again, the x value goes in everywhere you see an x. 2 times 0 cubed minus 4 times 0 squared plus 5 times 0. This is equal to literally 0, okay? So what is this saying right here when I get that? Well, really what this is saying is that when I substitute x in right here, this is going to shoot out a y value. You can think of this as being a y value, f of 0. So f of 0 equals 0. This right here is your y value. Okay? This right here, this 0 that's in the brackets, this is your x value. Okay? So again, we're looking to determine whether or not this is a root or 0 of a function. Because the y value is 0, that means that it is a 0 of a function. So at x equals 0, f of 0 equals 0. Lots of zeros in here. So it is the 0 of the function. Okay. It could have been, I could have put in, an x equals 10. And if you find that f of 10 equals 0, then x equals 10 would be the 0. Okay. Let's do another one real quick, so hopefully you can, just see another example in process here. All right, so let's do. Do I want to do that one? I'm gonna do 23. Okay. I want to do just another one. If you have a rational expression and you get a 0 in the denominator, again, that would be a no. So just bear that in mind. I don't know if that comes up or not. Y of s. Very clever use of variables here. Squared minus 2s minus 2, and they're asking at s is equal to 1. All right, so now we're going to substitute in y of 1 is equal to 5 times 1 squared minus 2 times 1 minus 2. What does that equal? So this is going to be 5 minus 2 is equal to 1, right? 5 minus 2 is 3, minus 2 is 1. So because I have y of 1 is equal to 1, this is not a 0. Okay. In other words, when you go through this process of solving this, you want it to equal 0 at the end in order for it to be a 0. That's kind of in the definition, right? It needs to be 0 for it to be a 0. That's just how it goes. All right, so that's 23. Let's go ahead and do, jump to my next page. Let's do one of these. I'm going to do 28. So given, in these ones, you're asked to evaluate the function at specific values, x values, or in this case, t values, it looks like. 3t squared minus t. So part A is asking us to find j of minus 4. Excuse me. So this is equal to 3 times minus 4 squared minus a minus 4. Okay. And this is going to be equal to 3 times 16 plus 4, which is equal to 52. Okay? So that is, you can think of this again as like a y value. My x value is minus 4. My y value is going to be 52. Part B, j of 0. All right, that one should be easy. 3 times 0 squared minus 0 is equal to 0. Nice. Part C. You know what? I'm going to skip this one. I think I skipped this one when I wrote the notes out. D. J of minus C. So again, it's the same idea. We're just going to substitute in this variable, minus c squared minus a minus c is equal to 3c squared plus c. So we actually just get another expression as a result of making that substitution. I'm going to do one last one, and then I'm going to jump to the next question. J of x plus h. All right, so here what we're going to do is, again, everywhere we see a t, we're going to substitute x plus h. So x plus h squared minus x plus h. Okay. This is going to equal 3 times x squared plus 2xh plus h squared minus x minus h. So I just did that's actually one of those special cases of multiplication. If you maybe have memorized it, I don't know if you have, but that's what you'll get if you go ahead and FOIL the whole thing. So here we're going to have 3x squared plus 6xh plus 3h squared minus x minus h. And yeah, that's it. I can't combine or merge any of those together. All right, so that's 28. Let's go ahead and keep moving on. All right, we're at 42 minutes. Can I make it an hour? I don't know. I hope to make it under an hour. I think I can do that. Let's just give it a shot. So question... So these next questions are going to ask us to determine the domain. So for question 38, f of x is equal to 3x squared plus 1. And again, remember, this is not any of those special circumstances. The special circumstances being something regarding a piecewise defined function, which I don't even think there's any questions regarding that here. So you probably will never have to deal with that one. If you have a rational expression, in other words, a fraction, which this is not, so we don't have to worry about it, and we do not have a radical expression, which means it's underneath the square root. So in this case, the domain is going to be all real numbers. Okay? If you have to write it in interval notation, it's going to be between negative infinity and positive infinity. Okay? That just means that your every single value is going to be represented. All right, so let's do question 40. I've got f of x is equal to 6 over x minus 5. So what does this mean? Well, now we've got one of those special cases. We've got a fraction. So the thing that we do, remember, we need to find the critical values. The critical values here are going to be x minus 5 cannot equal 0. So x cannot equal positive 5. Okay? So in other words, the domain, I think I teased this earlier, is going to be x, so we're going to write it in set builder form, such that x cannot equal 5. Whoop, my squiggle. All right. And if I wanted to write it in interval notation, I would go from negative infinity up to 5, open bracket right there, union 5 to positive infinity. Okay. All right, so those are two questions there. I want to do a radical expression just so you can see how to find the domain on one of those. So 42, f of x is equal to the square root of 4 minus x, okay? So what do we do with this? When we're looking for the domain, remember we're only dealing with real numbers. No complex numbers whatsoever, no imaginary numbers. So that means that whatever sits underneath that radical expression, it has to be positive. 0 or positive, I should say. So when we see an instance like this, we need to take that expression and set it greater than or equal to 0. So we are solving this inequality right here. So we'll let's just move the minus x to the other side. That way we've got this, and I'll just do it like this. Okay. These two are exactly the same. I just flipped the order. So that right there is our domain restriction. So the domain here is going to be x such that x is less than or equal to 4. Okay? Or what you could say is from negative infinity all the way up to 4. And that's going to be a square bracket. All right, let's go ahead and take a look at something that combines both radical and rational expressions. 46. F of x is equal to 1 over square root 5 minus x. Okay, so when we have a fractional problem like this, we cannot have the denominator equal to 0. When we have something with a square root, everything that's underneath it has to be greater than or equal to 0. So you can see that there's a bit of a problem here, because if I have something that's greater than or equal to 0 right here, I still might potentially get a 0 in the denominator. So to remedy this situation, when we have both of those cases, we're literally going to take the same thing that we did the last time, and the only difference is we're not going to include the equal. Right? Because if I set it equal to 0, that means that my denominator could potentially be 0, and I do not want that. So we're just going to exclude the equal from that specific one. So here we're going to have 5 greater than x, and then I'm going to flip it, x, which is less than 5. Okay? So again, the domain in this case, x such that x is less than 5. That's the set builder way of writing it. Or you can do negative infinity to 5, and it's going to be open brackets. So these are, again, are just two ways of writing the domain, but really this is one of those cases, again, that involves multiple multiple considerations. You got to think about just all the ramifications of that problem. Okay. All right, moving on. Let's see here. Oh yeah, okay, I want to do one of these. 64. This is just one of those really long sections, guys. I'm really sorry about that. F of x is equal to 2 minus 5x. F of a is equal to 1, okay? So what we're going to do is, you're probably wondering, what the heck is this thing even asking? The question says to find the value or values of a in the domain of f for which f of a is equal to the given number, okay? So long story short, what we're doing is we're substituting a in for our x value, and then we're setting the entire thing equal to whatever is on this side right here. I think I wrote that wrong. I think this should be set. Yeah, this should be 7. Sorry, that's a 7. All right, so what are we doing? F of a is equal to 2 minus 5. Again, we're substituting a for x. A. we know that f of a is equal to 7. So now I'm just going to do 7 is equal to 2 minus 5a. And what does that mean? Now I move things around. Subtract 2 from both sides. I'm going to get 5 is equal to a minus 5a, which means that a is going to equal a minus 1 when I divide by a negative 5. So that's 64. A is equal to negative 1. Let me do one more of those. We'll do 66. F of x is equal to x squared minus 5x minus 16. And f of a is equal to negative 2. Okay? So f of a is equal to a squared minus 5a. See, 5a. I see I made the mistake right there. Every x turns into an a. Minus 16. And now I set that equal to minus 2. A squared minus 5a minus 16. In this case, my suggestion would be just to balance this out. So I'm going to add 2 to both sides. Minus 5a. Adding 2 is going to make this a minus 14. And now I can factor, okay? So 0 is equal to a minus 7, a plus 2. And when I set these both individually equal to 0, again, if you're like, dude, you're going way too fast, just slow this thing down or go through it a couple times because I just do not want to make this video way too long. A is equal to 7 and a is equal to a minus 2. Okay? So these are the values that we get. So that's 66. All right. Are we near the home stretch? I promise we are. Can I get this done in the next 6 minutes? We're going to sure try our best. All right, let's do... Oh, yeah, okay, so 72 is saying find the zeros, okay? 72, find the zeros. Okay. F of x is equal to 6 plus 2x. 0 is equal to... So what we're doing is we're going to set this guy equal to 0, okay? When we're finding the zeros, we're setting what's on the other side of the equal sign equal to 0. That's kind of what we were doing the last time, like earlier, when I was saying, hey, like the 0, set this thing equal to 0. If it's 0, then you know that it works, right? Same idea. We're setting this thing equal to 0, and then we're just going to solve. So now I just move the x and the numbers around and see what I get. So let's just move the 6 to the other side. We'll divide through by 2, so we're going to get minus 3 is equal to x. So x is equal to minus 3. Okay. So that right there is the 0. This is the 0 of f of x. All right. That was 72. 76, real quick. I can do this real fast, I promise. F of x is equal to x squared plus 4x minus 21. Again, we're finding the zeros, which means what I need to do is set this equal to 0. And I'm going to factor this, actually. So the factors are going to be 7 and 3. Again, 7 times 3 is going to be 21. A combination of 7 and 3 is going to produce 4. Since this is negative and that's positive, that means that the bigger number is going to be positive. So this is going to be x plus 7, x minus 3. Okay? So now I set both equal to 0 and solve. So x is equal to a minus 7. X is equal to a positive 3. Okay. And those are our solutions to that problem. Those are the zeros of that problem. All right, let's look at 81. Here they actually are just showing us a graph. They don't actually tell you what the function itself is. Excuse me. Whew. Oh, I was going to show you something, by the way, on Wolfram Alpha. Maybe I'll do that here in a minute. So here they show you that the function, so here's our y-axis, here's our x-axis. This is -1, and looks like 1, 2. My scale is all jacked up. Sorry about that. -2. So it looks like we have a parabola that goes kind of like this. Okay? So this is our function. They call this f. And what they're doing is they're telling us to find the location or where it's increasing and decreasing or constant. Okay? So for question 81, I guess the book, I just want to clarify something. I guess the book is saying that it can't be constant at that value, at any specific particular value, which it's technically not correct, but I'll just go with what the book says because that's what the homework says. So okay, so here's what's happening. It's going to be decreasing if you follow the where it's going from left to right. It decreases down to that minimum point. So what's the interval that this is decreasing on? Since this function goes back perpetually all the way to -infinity, and again, we're only thinking about x values here, okay? What that means is that from -infinity up to 0, okay? And they're saying that it's including 0, but that's fine, decreasing. Technically, at this point, it's both increasing and decreasing, which that's technically constant, but whatever. This is how they want to define it. So this right here is going to be decreasing, okay? And this one is going to be increasing all the way up as we increase from the left to the right, all the way up to positive infinity. So from 0 up to positive infinity, we have a function that is increasing. Okay? So you're just looking at the behavior, the far left and far right behavior. What happens is you take it all the way out to infinity in both directions. Is it increasing? Is it decreasing? What's going on? I got 3 minutes before an hour. All right, yeah, actually, I want to do this one because this is actually a pretty good one. Real quick, this one is surprisingly, well, I'm just going to make it up. A cubic function. So actually, this is not in your book. I'm just making this up literally as we go. X cubed looks like this. So here's our y, here's our x. So the question is, what is happening? Is it increasing or decreasing? Again, as I read it from left to right, what's happening? So start on the far left of the graph and then just trace your way up. What's happening? It's increasing, right? What about when I get here? Technically, according to the book, it is still increasing. But what about as I keep going? It's still increasing. So this cubic function is technically increasing from -infinity up to positive infinity. Okay? So another way you can say it is that it's increasing along the entire domain or on the entire domain. Okay? That is all we're going to do here today. Like I said, a very, very, very long video, but if anybody has questions, feel free to email me. Hopefully you can use this as reference in the future if you get stuck on stuff, but let me know, and I hope you have a great day.